Alright guys, we're going to talk about ionic bonds and ionic compounds today. Now, the formation of an ionic bond. First we need to know what that is. An ionic bond is a force that holds oppositely charged particles together in an ionic compound. So if you have oppositely charged particles, that means an ionic bond has a positive charge and a negative charge. So that automatically means you should know what type of elements make up an ionic bond. It means that we're going to have one metal and one nonmetal, since it's going to be one positive and one negative charge. So as you can see here, this is what we just talked about, but ionic bonds are formed between a positive and a negative charge, which means they're composed of metals and nonmetals. Now, an ionic compound are the compounds that contain these ionic bonds, okay? So a compound is going to have many of these bonds all together. You've got to remember that ionic is between a metal and a nonmetal, because later we're going to talk about covalent compounds, and those are between two or more nonmetals. So you're going to have to know the difference, so make sure you remember this. Now, in an ionic bond, electrons are transferred. That's how electrons move in an ionic bond. They're actually transferred from one to the other. And as you already know, the positive metal ion is going to lose its electron to the negative nonmetal. Now, binary ionic compounds. These are compounds that contain a metal cation and a non-metal ion. And the reason we say binary is because they contain only two different elements. All right? When we say tertiary in a couple, I don't know if it'll be this unit or next unit, you're going to learn what that means. But right now, remember that binary means only two different elements. So sodium chloride is a binary compound because it contains sodium and chlorine, which is only two different elements. Now, when we're looking at ionic bonds forming, it has to do with their charge. To show you how the ionic charge is used in the formation of these compounds, we're going to look at the formation of calcium fluoride. Calcium has an electron configuration of, and this is the noble gas configuration, or the abbreviated configuration. So it's argon gas, and then 4s2 is calcium. So that means that calcium has two valence electrons, and they want to lose those valence electrons so that they can have a stable electron configuration like argon. Fluorine has an electron configuration of helium 2s2 2p5, and if you'll look, since the second energy level is the last energy level in the configuration, that means it's its outer energy level, and it means that fluorine has 7 valence electrons. So they want to gain, that fluorine wants to gain 1 electron, so it has a stable electron configuration like helium. That's how calcium and fluorine make a bond, because calcium is able to give it 1 of its electrons to fluorine. We add another fluorine like we talked about in the last video, and calcium is able to add its last electron to it. Now what we'll do is we're just going to look at this again in the drawing and how to draw them to show how these bonds work. Okay, so again, we just want to look at this so that you can actually visualize it. So if we have calcium and we have fluorine, we're going to put our 2 valence electrons of calcium in the middle, and then fluorine has 7, so it has 6 on the outside, and then we're going to place 1 in the middle. So only 1 fluorine can bond to this calcium at the time because we only had 1, but we just add another fluorine because we still have an electron in calcium that's not bound yet. So that also gives us the formula, just to be practicing it. We have 1 calcium here and 2 fluorine. And so it's a 1-to-2 ratio. All right. Now, one more example, so we can just, I'm hoping that you already remember this because we should have practiced it a lot in class. But one more example, if we have lithium and fluorine, lithium has 1 valence electron, fluorine has 7, again. And so we can make 1 bond there to give us lithium fluoride. There's the formula, and it's a 1-to-1 ratio. All right, let's get back and finish our notes. All right, now let's look at properties of ionic compounds. The chemical bonds in a compound actually determine several of the compound's properties to help us know exactly what's going to happen. And the reason why, because you've learned so far that valence electrons determine chemical properties. So since the valence electrons are the ones bonding, that actually those bonds determine the compound's chemical properties. Now, ionic bonds produce a unique physical structure, and they're called, well, they're unlike any other compounds, and we call it a crystal lattice, which we're fixing to talk about. But the physical structure that the ionic bonds produce contribute to the physical properties as well as the chemical properties of that compound. All right, we just saw that, so let's keep going. All right, in an ionic compound, the large numbers of positive ions and negative ions exist together, all in one place. So these ions are packed very closely, and they're in a regular repeating pattern. And the reason they're in a repeating pattern is because the balances or the forces between the negative and positive ions have to be balanced. And so that regular repeating pattern helps to balance the forces out between that attraction and repulsion. So in an ionic compound, the strong attractions between the oppositely charged ions result in the formation of a crystal lattice. Now, a crystal lattice is a 3D geometric arrangement of particles, and you're fixing to get to see a picture of one. This is a picture of a crystal lattice of sodium chloride, NaCl. And in a crystal lattice, as you can see, each positive ion is surrounded by the negative ion. Now, chlorine are going to be the small purple, because remember, chlorine, since it's on the right side of the periodic table, is going to have a smaller atomic radius than sodium is. So sodium are the green atoms, and chlorine are the small purple atoms, and they are surrounded by the opposite one because of attraction. Now, the energy required to separate 1 mole of the ion from this crystal lattice is referred to as lattice energy. So however much energy I have to put into removing that mole is called lattice energy. The larger the size of the atom, the smaller the lattice energy. But the larger the charge, the larger the lattice energy. So making sure you know how those relate to one another. Now, there are 3 physical properties that are determined by how strongly the particles are attracted to one another. And these 3 properties are melting point, boiling point, and hardness of the ionic compound. Now, ionic bonds are extremely strong, which means it takes a lot of energy to break the bonds between ionic compounds. And that also means, since it takes a lot of energy to break them, it's going to give them high melting points and high boiling points, because temperature is a type of energy, or heat is a type of energy. So as you heat something up, if it's weak, it will immediately melt or disintegrate and break those bonds. However, if it stays together, that means it, against the strong heat, then it means it has a higher melting point and a higher boiling point, so it means it's stronger because those bonds can withstand the strong heat energy that's being placed against them. Now, one last physical property we're going to talk about, and this is determined by the presence of freely moving charged particles, and that's conductivity. When you have an ionic compound and it's solid, in a solid state, like salt would be that we use for our dinner, the ions in an ionic compound are locked into a fixed position, and they're not able to conduct electricity. They're in that crystal lattice that we saw earlier in the picture. However, if you take that ionic compound like salt and you melt it or you dissolve it into a solution, the ions are no longer locked into that fixed position. So then you have freely moving ions moving around that have charges. And that's what it's talking about up here when you have freely moving charged particles. Now what I'd like to do is show you an actual simulation of that. All right, so the first one we're going to look at is salt. So I'm going to shake some salt into our water. And we actually have a conductivity test we can do on the solution. So over here I drag my conductivity. And once I place it in the salt water, as you can see, it illuminates the light bulb. And we'll actually get to see this in class, but it illuminates the light bulb. So let's place our conductivity meter back. I'm going to reset everything and we're going to change it to sugar. Now sugar is made up of carbon, hydrogen, and oxygen. So those are all nonmetals. So they're covalent bonds. And when I put sugar into the water, I pull my conductivity meter to the water, and as you can see, the light bulb does not light up. So that tells us that covalent bonds cannot conduct electricity, but ionic bonds, once dissolved in solution, can conduct electricity. Now I want to show you why ionic bonds can conduct electricity and covalent bonds cannot. As you can see, when I place sugar, well, first of all, these are water molecules that you see in the main box. When I place sugar into the water, as you can see, it breaks apart, but it still stays large molecules. So they don't have oppositely charged ions freely floating around for electricity to be conducted through. Let's reset this, and I want to put the salt into the water. And as you can see, it actually breaks completely apart where you have positive and negative ions by themselves, and so electricity can be conducted through these freely moving ions. Now I also want to show you on where you can see it again. This is sodium chloride, NaCl. Sucrose is sugar. So when I put sodium chloride, the NaCl, into the water, see how they all break apart? And so they're freely floating ions, so electricity can pass through. However, when we change this to sugar, again, and you're seeing the same thing just on a different scale. As you can see, the molecules of sugar stay together, so they don't have freely moving ions. So that is why ionic bonds conduct electricity, but covalent bonds do not. Now, what I'd like you to do is summarize, make a summary, and I would like you to summarize in a TV catchphrase. And what I mean, sometimes a TV show or a news channel is going to a commercial and kind of give you a catchphrase that pulls you back in and wants you to stay watching. So what I'd like you to do is come up with something that kind of pulls someone's interest in about what we've talked about today. And I will see you in class.